All right, howdy everybody. In this video, we're going to talk through a synthesis problem, and I would put the majority of the content for the synthesis in a chapter relating to amines and chemistry associated with amines. And I would rank this one as being of modest difficulty, but hopefully one that after you study with and practice with for a while, that it'll all make sense. What I typically encourage people to do with these kinds of synthesis problems is to think through a number of the possibilities, but then also to try to recognize what some pitfalls are or might be in their proposed synthetic sequence. And so I'm going to encourage you to do that all on your own. And what's really important about actually pausing these videos to try to work through them all on your own is that's how you're actually going to build up that deeper understanding and learning. And then when you come back and watch the answers or discussion that I have for the problems, hopefully a couple more things will click. But it really is important that you actually pause these videos and try to attack these problems all on your own before you just watch through to the answer. And so please do that right now. Click pause, please. All right, welcome back. What I'm going to do here is talk through some of the possible solutions to this problem, and then hopefully identify a couple of the pitfalls that I've seen or suspect students would fall into in trying to answer this. And of course, going from this complicated tri-substituted amine all the way back to benzyl bromide, because we have the one aromatic group over here, we know that that will be the ring that ends up being there. And so that means that this carbon will end up being that benzyl bromide carbon. On its surface, this means that we have to do a couple of things, and ideally we're going to have to form not one, not two, but actually three separate highly selective carbon-nitrogen bond-forming reactions. And so let's just talk through what some of those are and what some of the common pitfalls might be down below. So one of the things that I try to remind students is if you have a molecule like ammonia and you expose it to a really good electrophile like a primary alkyl halide, where X here can be chloride or bromine or iodine, what you can end up with is not just, let's say, the desired amine product, because that would be okay, but often you'll also end up with the over-alkylated material. And so you can over-alkylate once, but you can over-alkylate actually 3 times. And so you can end up with the primary, secondary, tertiary, or quaternary amine as possible products of these alkylations. And so we try not to do these reactions with either primary or secondary, either primary or secondary amines or ammonia. And so it can work okay as long as it's sterically congested amine. But there are a couple of more efficient ways that we've discovered to do these. One common one that's talked about in most textbooks is the Gabriel synthesis. And this starts with typically potassium phthalimide. And you can buy potassium phthalimide from most vendors of chemical reagents. And so you can actually get a bottle of this salt. And it's stable under ambient conditions because the pKa of that NH is sufficiently low that it'll stay deprotonated in water. And so what you can do instead then is alkylate those same electrophiles with the phthalimide anion. And then you can deprotect this typically with hydrazine is a very common deprotecting reagent, and that will get you the NH2 primary amine. And so that's kind of the first way to circumvent this issue of over-alkylating and getting mixtures is to use the Gabriel synthesis. The second of these is actually to use an azide. And one safety note on azides is they can be explosive depending on the nature of that azide functional group. Now, my research actually involves using azides, and thankfully my lab hasn't had any issues over the last 5 years working with these compounds. But that being said, we do take a bunch of safety precautions. And so I'll just remind people, if you haven't heard that before, that the azide can be explosive, and so you want to think very carefully about the chemistry that you're going to do with sodium azide. That being said, it is a very useful functional group, and it can be converted from the azide to the amine in a variety of conditions. So the first one can just be PPH3, and so this is the so-called Staudinger reaction. Typically, then you use some water at the end to hydrolyze it. The second of these can be to use lithium aluminum hydride, and so that's a very powerful reducing agent. You'll see me in these videos comment that that's kind of our big sledgehammer reducing agent, and it knocks everything down. In this particular case, that includes the azide functional group, and probably most students' favorite is to use palladium on carbon with H2 gas. And so that's another very common way to reduce an azide to the primary amine. And so there's a lot of chemistry to do that, and it ends up being a very highly efficient reaction. And so either the Gabriel synthesis or the use of a primary azide can get us around this issue of amine overalkylation. So that's something that we really want to take into account in the synthesis problem that we're given up above. The other kinds of bonds here are going to be different. Is this one's a secondary carbon. And I'll remind people that the SN2 reaction on secondary carbons is often quite problematic. And it's problematic because the SN2 reaction, remember, can always compete with the E2 reaction. And so if you have something that's strongly basic and you're trying to use one of these strongly or secondary electrophiles, sometimes it can be hard to go to get it to do the substitution reaction. So this would be the SN2 reaction. And the reason why it's problematic is if we have that same X group here, we instead can have a base. And remember, most strong nucleophiles are also strong bases. Those two things tend to trend together. They're definitely correlated. And so what a lot of these bases do instead is they promote the E2 reaction. And so here then you'll have BH plus X minus is a salt, and then you'll make the alkene. And so because of that, it gets to be very difficult to do substitution reactions on secondary positions with amines. Okay, so those are some of our common pitfalls, but let's pick either one of our favorite kind of ways to introduce a nitrogen from the benzyl bromide starting material and just see where we can go. So if I start with benzyl bromide, I could take this up with phthalimide, potassium phthalimide. And then I can reduce this with hydrazine. Sorry, not reduce, deprotect it with hydrazine, and that'll get me benzylamine. And I could take the same starting material then and instead use sodium azide. And I can reduce that azide functional group to the amine using palladium on carbon with some hydrogen gas. And so either way, that would get me benzylamine, and so that seems quite reasonable. Now I have a couple of different groups to install, and if I go up here and look, you know, it could be this one first or this one. I will remind people, though, that once you make a nitrogen into an amide, and that's the functional group here, that's an amide, and once you make that nitrogen or incorporate that nitrogen into an amide, it tends not to be nucleophilic on nitrogen anymore because we have this resonance structure where the N lone pair can delocalize into the oxygen. And so amides tend to actually be basic on their carbonyl oxygen. And so because of that, if we want to use that site for a nucleophile, we probably want to avoid making the amide first. So that means that we would want to make the cyclohexyl group first. And so then, and because of this E2 issue that we talked about here a minute ago, we probably want to avoid the SN2 reaction. But there should be another way that we know of to make carbon-nitrogen bonds, and one that comes to mind is reductive amination. And so if I started with the cyclohexanone, I should be able to condense this to the imine, and then reduce that imine with a variety of reagents. Now, a number of reagents are powerful enough to reduce the carbon-nitrogen double bond, but one that we really like in the lab, let me just make this arrow a little bit longer. We really like sodium cyanoborohydride, or sometimes we use sodium triacetoxyborohydride. And so either of these are very common reagents for reductive amination. And the reason is because they end up reacting selectively with, after this gets protonated, the iminium ion. And so the iminium ion is much more electrophilic than the imine. And so it tends to be the actual intermediate that's reduced by these weaker, much more selective reducing agents, sodium cyanoborohydride and sodium triacetoxyborohydride. And so because of the unique chemoselectivity offered by these very mild borohydride reagents, it turns out to be really great to do this reductive amination. And often you can just mix the amine and the ketone together in the presence of one of these reagents, and when the iminium ion forms, that'll be what gets reduced. And that keeps the ketone from being reduced faster. Okay, so this then would make our cyclohexyl benzylamine. And what's convenient about this is then we're just one acylation away from the final product. And so let's go ahead and put all these things that we've talked about back into the blank. And since my lab happens to use azides, I'm going to use sodium azide here. I'm going to use palladium on carbon with H2 gas. And then I'm going to use cyclohexanone as a reagent, and I'm going to use sodium triacetoxyborohydride as the reducing agent for the reductive amination reaction. So that gets me most of the way there, and then we can make an amide with our acetyl chloride and maybe some triethylamine as the base. And that'll mop up the HCl that we formed from this reaction. Oops. And I think that wraps it up. So overall, hopefully in this video, you get a sense for how we can think about how to order which groups we should bring in, and as well as a reminder for some of the kind of common pitfalls for synthesis of amines, one of which is the overalkylation of nitrogen, and the other of which is this pesky issue of wanting to do an SN2 reaction, but getting the products of an E2 reaction instead. And so just as a reminder, remember SN2 works great on primary carbons. It's a super problem on tertiary carbons, and most of the time it doesn't work too well on secondary carbons either. All right, hopefully you've enjoyed this video. If you're getting use out of these videos, please do subscribe to the YouTube channel. Again, that's one way where we know that you're watching these and that somebody is taking advantage of the resources we're putting out there. If you find it helpful to get these notes either before or after I've filled them out, please go ahead and subscribe to us on Patreon. And we're also more appreciative of likes on Twitter or Facebook. And so please do follow us on your favorite social media channel as well. All right, thank you. Watch the next video and please tell a friend about us.